Hello, everyone. I am guiltygyoza from Topology, and today I want to share our learning from the Shoshin experiment. So, since the genesis of topology, we have been exploring what does it take to realize our vision, which is building these um, interconnected and composable virtual worlds on a strongly decentralized basis, presumably on the blockchain. And this is a really big undertaking that covers many different aspects and disciplines. And there's the word cloud that we are holding in our head at the same time. There are a lot of subjects we need to tackle. This slide lists some of the subjects that we have tackled in the past roughly 2 years. Verifiable computation is one of the major topics because blockchain gave us verifiable compute via coordination and consensus. With zero knowledge proof, we will be having verifiable computation, but with the magical asymmetry, so that the verification part is very cheap, and we are we are very happy about it's almost, to us, we feel that it's fortunate to live in this period in the history where we are exposed to this new technological primitive, and we can do something about it. And we want to apply it to building composable, interconnected virtual worlds. So that's one basis. Other topics include digital physics, which basically means that in these worlds that people will build, they will have their own laws of physics. And unlike this reality where we are born into, we're thrown into this world where the laws of physics are presumably fixed, invented by some entity that no one truly understands, and we can only study it and model it. But in these virtual worlds that we will be building on a strongly decentralized basis, which means we can be the owner of the world, we can be self-sovereign, governing the world. We dictate the laws of physics in these worlds that we create. So digital physics is this idea that you design your own laws of physics, but how and specifically what can be done, what can be created and enforced on a strongly decentralized basis. Digital means that because we are running these worlds on digital platforms, these physics are digital first. Whereas in our reality, I like to call our physics the analog physics, the physics that is almost perfectly continuous. Of course, there is probably the smallest scale in time and space, but in the human dimension, those scales are negligible. So to us, this world is continuous. But in the virtual worlds, everything is running on a digital basis and hence discrete, and it follows a very different kind of dynamics than in our reality. So that's digital physics. Distributed creativity is this idea that really players have immense creativity, and there's this asymmetry between traditionally in video games where video game developers provide you with primitives and rules of the game and building blocks in the game to play with, and the players are sort of constrained but also enabled by those building blocks to express their creativity. Distributed creativity means that some of these building blocks were previously built and controlled only by the game developer. But what if we can give every player tools and interfaces so that they can make building blocks in video games in these worlds, on top of which more emergent behaviors and complexities and richness is possible. So we are sort of distributing I'm not sure us deeply. And then in between these subjects, there are many smaller subjects and interesting topics. From top to bottom, we have playable characters because in an agentic computing environment, users or entities are embodied, and so there are the notion of characters and hence playable characters. And there are autonomous behavior that are driving the characters that are not playable, meaning they are driven not by human users, but by autonomous agents and behaviors. And then there's the notion of composable engineering, which means that based on the laws of physics in a given world, I can engineer stuff as long as the stuff follows the laws of physics. It can work anywhere, anytime, and it can be building blocks for other inhabitants of the world to create, compose into bigger building blocks and with different kinds of utilities and usage. So that's composable engineering. Spectator value means our interest in making demonstrations that have high watchability. High watchability means that even if you are not directly participating in sort of the intensive activity or sort of the primary participatory mode of the world, merely by spectating, would you also be able to derive pleasure and derive engaging feelings? So that also makes the particular digital world or autonomous world, if you will, more interesting. Shoshin is our latest experiments that explore a lot of the subjects in the previous slide all at once. Here you are seeing Antok and Jessica, the two characters battling. This is not a real-time fighting game that we're making. This is a game where physics and agent behavior simulation all happens in the Cairo VM, hence verifiable compute. Physics is written in Cairo, and therefore we have the digital physics of the Shoshin world verifiably enforced. The game is not played by real time because really it's played by players designing the strategies that control these behaviors. And we'll be seeing what the strategy means in a later slide. But essentially, this is a synchronous game. You play, players play Shoshin not by using their keyboards and mouse in real time. Instead, they design strategies and submit asynchronously. And then the fight begins, pitting two strategies together, simulate the fight and the outcome. So we derive two major learnings from this Shoshin experiment. The first one is, if you want to provide programmability without programming, you might want to run your own app-specific computer in the VM. And the VM here means a VM that is replicated, presumably a blockchain VM. So what do we mean by providing programmability without programming? Well, coming back to distributed creativity, players have creativity, but a lot of people in the world do not code. They don't program computers. And in fact, I think programming computers is kind of a very unintuitive thing for humans, because programming computers most of the time requires you to linearize your thoughts and to sort of not think in an associative way, but in think in very mechanical ways. And it just requires a lot of mental model exercises, a lot of training to be really good at programming. And if you want to tap into player creativity by asking them to program, then that's not a very accessible approach. So we want to essentially give players to express creativity, and the most flexible way to allow that would be to give them some kind of capability to program, but we don't want them to program per se. And so what we really need is we need to have a game-specific computer on top of which we can allow player to program, but not really programming, because we're exposing a different kind of API that is more humane and more intuitive to regular people, non-programmer intuitive thought process and thought patterns. So this is one of the original inspirations that influenced us very much. Robot Odyssey, a game from 1984. This is a game where you are solving puzzles, but you don't solve the puzzle by controlling these submarines and these robots in real time. Instead, you design behaviors, you design sort of circuitries that will basically dictate the behavior of the robot in order to solve the puzzle. And you can see here that a robot has different sensors and has different actuators. So sensors basically allow the robot to perceive from the environment. Actuators allow the robot to change its bearing and its relationship with the environment. So a sensor is for input, actuator is for output. So what's inside the robot? Well, this is what the player designed, circuitry, and they weren't kidding. These circuitries are literally Boolean circuits. So you would have logical gates that take binary signals, and you're supposed to create these gates and connect them in order to form meaningful logic that can make decisions based on perceptions, and use the actuator to move your robots and interact with different traps and other robots to solve the puzzle. Obviously, this is a programming homework, more or less a sort of a training course, but gamified version for electrical engineering, I would say. But this game has a little cult to itself. People who love this game really love this game, but I believe for most of the players, this wasn't really an approachable experience. Right. So on the side note, we also want watchability. We want to make an experiment that focus on tapping into player creativity, distributed creativity, but we also want the outcome of sort of that creativity expression to be highly watchable and interesting. And so we like fighting games. We chose fighting game as a genre or a pattern to explore player creativity. And this is Street Fighter II, 1991, the classic sort of the fighting game that defined the beginning of a genre. Of course, there are fighting games that came before Street Fighter, but Street Fighter II was sort of this canonical. Everyone knows the game. It is the grandfather of fighting games. Okay, so inside Shoshin, we want two characters to fight against each other, and each agent, essentially, agent is something that can perceive from the environment and make action, right? So you have agent one and agent two, both perceiving from the environment and both each controlling their own character. Perceptibles one fed into agent one, and you will notice that perceptibles one is different from perceptibles two because these agents have certain perceptibles that are only for themselves, that are not for the other side. So, for example, which animation frame am I in? Some of these perceptibles are only for yourself, not for the opponent. And once perceptibles go into agent, logic, the logical machine starts churning, and actions are made, and these actions drive the character. You can see the character as a body that receives the motor signal from the brain, and then it moves its limbs. That's the character. And then once the two characters are moving and they make their sort of physical motion, a physics simulation happened at the end that sort of merge these character movements and simulate the outcome according to the digital physics, the laws of physics in the Shoshin world. And this entire pipeline happens every single frame. So, for example, if we simulate the game for 430 something frame, which given our frame rate roughly accounts for 30 seconds worth of fight, this flow is the game loop that runs every single frame, sort of in an auto-regressive fashion. Basically, that means that the frame one's output is fed into frame two's input, and so on and so forth. Okay, so now the meat the elephant in the room is distributed creativity, programming without programming. How do we do that? So this is in Unity where people can create agent behaviors. So agent will have different mode of behavior, and depending on how players interact with the agent, most likely the NPC will transition to different mode and behave differently, right? And so, for example, you would have an enemy NPC that would sort of be on a patrol mode by default, and when the player is in line of sight, the NPC transition into a offensive mode or aggressive mode. And if the NPC's HP go below a certain level, the NPC transition to a defensive or fleeing mode. And in different mode, the NPC will have different behavior. Right, so this can be understood as a finite state machine. Well, it's a flow chart, is a finite state machine. It can be hierarchical or not, but essentially it is a state machine. In Unreal Engine as well. So this is animation state machine. This is I believe is a plugin to the Unreal Engine where people can use finite state machine semantics to describe behaviors. And finite state machine again is sort of the description of a system where a system can transition between state, and at any given moment, a system occupies a single state, and there are rules and conditions upon which the system transitions from one state to another state. Okay, so we decided to adopt finite state machine to pick something that is we believe, the most intuitive sort of system model to describe dynamic behavior. And we had to essentially implement a finite state machine computer in Cairo VM so that players, as long as they feed us finite state machines, we can compute it and we can calculate the agent's action. So essentially, players' output is a finite state machine, which is fed to the game loop, and the game loop every single frame churns the state machine, feeding perceptibles into the machine, churning it, and computing the actions, which is the action that the agent wants to take, which drives the body, which drives the physics. And these are some technical details that basically explains how we model the transition function between state machines, because we essentially need to give player a high degree of computability, but not Turing completeness, but a high degree of flexibility to express arbitrary functions. And so the data structure we chose was a binary expression tree. So as long as your state transition function can be expressed in this binary expression tree, given these opcode that we provide. So we have a series of opcode that allows you to construct trees that are used to express your state transition function. Of course, these opcodes constructions are handled by the game itself. On the player side, the players are exposed with a different interface that allows them to create state machines. So this is essentially the technical inside of a Shoshin, but the learning here is if we want to program programmability without programming, without forcing the players to program, we need to have a special kind of computer, which exposes a special kind of API that is more intuitive and easier to understand than sort of blatantly Turing complete programming. And then the next lesson actually follows the first lesson, which is if you want to make the game harder, you have to make the game easier to play. And what we mean by that is even finite state machines are too difficult to understand for most non-programmers. For example, what you're seeing here is sort of the one of the earliest generations of the Shoshin front-end interface, where the distributed creativity actually happens. And you can see we naively put a editor interface directly inside the front end, and this is basically players can program these different conditions. Conditions are basically sort of looking at the perceptible, sort of the observable variables of the world, and checking if something is true or something is not true, and sort of make decision based on those conditions or signals. In another word, we have non-programmer playtesters saying they don't recognize the symbol. What do you mean by two equal signs? So some of these things are very intuitive and taken for granted by programmers. They are very abstract and look very strange for non-programmers. We have to accept the fact that if we want to tap into sort of more broadly the kind of distributed creativity that we're looking for, we need to make it much simpler. This is the interface for players to create decision trees. So basically, if this condition is true, go to a different state. Otherwise, if the next condition is true, go to a different state, and so on and so forth. Again, these abstract symbols were proven very alienating for non-programmer players. So we had to do better. This was our attempt to visualize the state machine as a graph. So maybe the players can look at the machine and sort of intuit about transition between states and imagine in their head what the behavior might be. Still, this looks interesting to engineers, but very intimidating for non-programmers. So we have to do a lot better. Another note I want to make here is that because this is so hard to play, the game becomes easy. Easy in the sense that if you can't really explore the depth of the game becomes not engaging. And if you play 5 minutes worth of the game, you don't think game is interesting or deep or really hard. You just think the interface is really hard to use. So it is hard. The game is so hard to play. You feel like the game is easy. You don't appreciate its potential depth. So that's what we mean by if you want to make the game harder, more engaging, and deeper, you have to make the game much easier to play. So we had this reference to Final Fantasy XII's Gambit system, which is essentially an interface for players to program behavior. So if this condition is true, do something. If this condition is true, do something. There's no notion of finite state machine here. It is just a linear list of prioritized condition action pairs. So one condition goes true, do the associated action. Otherwise, check the next item down the list, and so on. So we were originally, ironically, very repulsed by this idea because we thought it is oversimplifying the situation and it might hurt just the kind of gameplay behavior that we were really looking for. But then we eventually accepted the fact that if players feel this is too hard to use, they would never really fully explore the depth, and there was no point. So we decided to give them a much easier interface, following inspired directly by Final Fantasy. So then we have these Gambit system. This is a screenshot from our front end prototypes where you have layers of condition and actions, right? If close is a condition, if it's true, then the agent will move backward. And then it sort of evolved into this situation where conditions can be composed because we kind of don't want player to write essentially a full sort of algebraic expression here in a condition. Because that becomes programming all over again. It becomes like a little math homework here. So instead, we want them to be able to sort of take these intuitive, super simple conditions and compose them into more interesting conditions that they want. Where each sort of atomic condition is very easy to understand. And then we added more features such as inverting a condition because we really don't want exclamation mark. Right? Exclamation mark might be inversion for programmers, but it looks very strange to non-programmers. We don't want that. So we introduce just more intuitive interface for non-programmers to feel easier. And there are other switches, which I won't cover here. These are really specific to fighting game behavior transitions, sort of out of the scope of the talk here. This is the sort of the final state of the Shoshin interface, where you have layers upon layers upon layers, and this was created by a real player of Shoshin during a tournament that we hosted during the Stanford Blockchain Week a month ago, roughly. And you see players are able to express very interesting and meaningfully complex thought process where you have the first condition is if my enemy is within 100 units from me, and if my enemy happens to be attacking, then I will dash backward. And this being an order one layer means it's like a highest priority. Right? And then you move down to the second layer, which is if my enemy is within 120 units from me, and if my opponent is jumping, then I have a mix-up. Mix-up is sort of this randomness. You would throw a dice, and 50% chance you will do upswing. Otherwise, you do a side cut. So you can mix up your behavior and make yourself less predictable. All these were added much, much later. So we really progressed from these sort of sugar-coated but blatantly programming homework kind of interface all the way to this still programming. I think for programmers, if programmers play the game, they still feel like they're kind of programming. But for non-programmers, they feel much more comfortable. And with this interface, although it looks simpler, it actually makes the game harder because now you have more players playing and more creativity involved are expressing themselves, and therefore you get more interesting and engaging fight. And as a result, this was one of the, I believe this is a semifinal fight during the Stanford Blockchain Week tournament that we hosted. You can see there are two Jessicas that are trying to get an upper hand against each other. And this really is a resource management game. If you look at the green bar, the green meter below the health meter is the rage meter. Spending half of your rage meter allows you to perform a ultimate move, which is really strong. And so this game almost becomes a resource management game where you want to get your rage up and you want to protect yourself from being attacked by the ultimate of the opponent. We didn't know about this until very late when a lot of players were playtesting this. And the reason why a lot of players were playtesting is because we made the game much easier through sort of a lot of iterations. And that at the end makes the game much harder because more creativity were expressed and more interesting player behaviors are being manifested. So that is my talk. Two primary learnings from Shoshin. I hope you learned something from it. Thank you, everyone.
Yep. Are any questions that you would like to ask Guilty?
Yeah, like, where do you plan on going from here?
Sorry, there was a little bit of echo. Oh yeah, Hanson, could you help repeat? Thank you.
I was just asking where you're going from here. What's next?
Hanson, could you repeat? I think you're closer to the microphone. I can hear you. Yes.
So he asked, what would be the
Yes.
future steps onward from here?
What would be the next steps of the experiment? Is that?
Yeah.
Yeah.
I see. So after the tournament, there was we learned a lot from the tournament, and we were internally discussing, and there's a lot of we were really much enlightened by a lot of these experiments and the learnings they brought us, and we've been saying that we are making games not for the purpose of making games, but these really to us experiments. What we really, the North Star for us really is to figure out what is the missing technologies or design approaches or techniques required to make scalable, interconnected and composable virtual worlds that are on a strongly decentralized basis. And I think that we might be really close towards figuring out the missing techniques and technologies. And so I think at the current moment, we are not actually working on the next iteration of Shoshin. Instead, we are in more rabbit hole and we're back in research mode because the learnings from Shoshin and some other thinkings are propelling us to do more research. And I think that our entire team should be attending the Dev Connect in Istanbul in November, and we will be excited to share what we learned and what we studied.